Wave fronts and rays. Elastic deformation advances in elastic media in all directions, up to distances in a given time which depend on the velocities in these directions. When the velocity of elastic wave propagation in a given rock is constant in all directions, it is said to be a uniform medium. In seismic prospecting, generally such an assumption is made. The surface obtained passing through all the points up to which a given elastic wave traveled in a given time is evidently spherical. This frontal surface of a wave is also called as wavefront. It is to be noted that the directions of propagation are perpendicular to the wavefront surface. These perpendicular paths along which elastic waves travel are known as rays. Elastic waves used in seismic prospecting are referred to as seismic waves and their propagational paths form seismic rays. The propagation of elastic waves in the Earth is governed by the Huygens and Fermat's principles. The Huygens principle states that every point on a seismic wave front may be considered as elemental seismic source, radiating elastic disturbances in its vicinity. Thus, if at any moment the location of a wave front in a given medium is known, it is possible to locate all other wave fronts at other time moments from a knowledge of the velocity distribution. The Fermat's principle states that the seismic wave propagation between any 2 points is always along the minimum travel time path. In a uniform medium, this implies the propagation of seismic waves along straight line paths. Elastic wave velocities in rocks. Since only compressional wave is used in routine seismic prospecting, elastic wave velocities are often described in rocks keeping this wave in view. The compressional wave velocities in different rocks vary over wide limits. These velocity variations are not only due to the compositional differences, but also due to their differences in porosity, saturation and compactness, which again depend on the age and depth of location of rock formations. It is evident that depending on these factors, the velocities in one and the same rock also may show variations. The product of elastic wave velocity and density of rocks is known as wave impedance. The differences in the wave impedances of individual rock formations in a layered sequence determine the possibilities for successful application of one or the other of seismic methods. The ranges of velocities and wave impedances, also known as acoustic impedance, for some typical rocks are as follows. In general, igneous rocks have a velocity range of 4 to 7 km per second, metamorphic rocks between 4 to 6 km per second, dense detrital rocks have velocities in the range 3 to 6 km per second, and the loosely packed rocks exhibit velocities less than 3 km per second. As the absolute age and depth of burial of a rock increases, velocity also generally increases. Empirical formulae giving velocities depending on these factors have been evolved for different rocks. Porosity and fissuring reduce the velocities, and increase of saturation results in a general increase in velocities, depending on the fluid filling the pores and other factors. It may therefore be seen that while the subsurface structure can be brought out by seismic prospecting, similar unique interpretation of the geology of the individual layers on velocities becomes difficult.